And then we also do believe that we must defend our own privacy if we expect to have any. So there's a privacy aspect here too. So collecting payments through these online payment processors like Stripe is pretty convenient for us, but it is going against what we want to be doing in this world. So in this cryptocurrency world, we do have to remind ourselves that privacy matters. And so how do we work around this particular problem? We wanted to see if we could come up with a way to accept private payments for our subscription service that also protects privacy. So that brings us back to the topic of privacy by design. So we thought, yeah, hey, we need to do privacy by design if we're thinking about solving this problem, right? We have this great opportunity to disrupt the status quo, to do something different, and better than Stripe, and to incorporate privacy from the beginning of our designs. And we have these grand visions of, all of us here are working on some project or watching some projects that have grand visions of changing the world. So if we want to change the world, we should also think about how we want the world to be and if privacy is something we value that needs to be incorporated in the beginning. We don't want all of our subscriptions to be public knowledge. We don't want to leak data in the process of paying for these subscriptions. And we also don't want to leak things that could be correlated with other data that could then become personal data about us. So a good example of how we like to think about this is HTTP and HTTPS. We all built the internet with HTTP. Now we've switched to HTTPS, and we realize that that's better. How about we do that the other way, like start with the HTTPS now? And so that's what we are trying to think about with how we approach this. So to talk a little bit about, just quickly, about what we are trying to add the subscription service for is our S4 product, which is Simple Secure Storage Service. I'm not trying to do marketing or anything, but it's important to understand the security principles that are behind it and how it functions, because this really ties into making having private payments be so important to this type of particular system. And so it does incorporate, it's basically capability-based security, and it has client-side encryption. You have to have the capability to access it. There's no logins, there's no passwords and things like that. And so because of that, we don't have any personal account information on people. There actually just isn't account information in general, which is nice. And so the ciphertext is stored with servers that we take care of. The servers are what I like to call stupid, but they don't know what they're storing. They just have shares of ciphertext. And they don't know, they know enough to like put it back, the client side is what puts it back together and decrypts it, and the servers know nothing about this. So this is good security properties, and it has good privacy properties. So yeah. And then we have the payments where we're using Stripe. Really not cool. So payments by subscriptions. This is important. We need to accept these payments for a subscription business model. And to go over that real quick, it's just that these payments need to repeat at specific intervals. And they need to be related. There are many variations on how merchants would prefer to manage these subscriptions. It can get kind of complicated, and they want to offer various options for the plans, maybe different periods that they need to repeat. And all of that, we want to try to make sure that there's not a relationship being built that could then become data that you could look at to then deduce who somebody was based on their behavior of paying the subscriptions. So there's a privacy concern there too. But for us, it really does seem that the subscription business model is a good fit for what we're trying to do. So yeah, this is why we have this problem. And blockchains right now, most of them do store data publicly, and most cryptocurrencies have personal data in the transactions, so we need cryptocurrency with privacy. And you guys have heard of Zcash. So we started looking at Zcash because we know that it's got these privacy properties in the transactions that we would like, the Zcash, the shielded transactions. And so we also, as a side note for disclosure, Zcash company is a sibling company of ours. But yeah, so we've been talking to them about this, and this is just a quick rundown of what Zcash is. I won't spend time on it because I think somebody else did earlier, somebody from the Zcash team, and they're here. But yeah, so the shielded transactions offer us a particular type of zero knowledge proof called zk-snarks, and when there's a Zcash transaction, there is an existing string of data that the sender of the transaction provides, the zero knowledge proof, along with the encrypted transaction data, which provides properties of the encrypted data cryptographically. So this assures ownership over the spending key and allows for verification for the transaction is valid, while preserving privacy of the transaction details. And the sapling release that's coming in a few months will also make this faster to use. So we've been looking at that goal for ourselves about like how can we implement something that's actually usable around the same time as sapling. And that's usable today because, you know, we want to use it now. So yeah, so now it's expensive to make things private and it's cheap to make things public. And we need to change that. One of the current, yeah, sorry, I lost my net place. Okay, now into the difficult part of putting all the pieces together. So using cryptocurrency for subscriptions, this is getting into the real problem that we have. So one of the current uses of Zcash shielded transactions is to have people prepay for subscriptions. This is out there being used by some people, and this works really well for service offerings where you can just shut down the service, but this doesn't work so well for us because then we're left with a bunch of ciphertext that belongs to somebody, and we're not quite sure what if they want to pay a month later or something. So it puts us in a weird business situation that we wanted to see if we couldn't work around that too. And this doesn't work, and this also is, another option would be to use something like smart contracts for managing subscriptions, but yeah, the privacy problem is there too. And then, yeah, and another option is the post-paid charging for use, but this also has the same kinds of problems as like the prepayment. And then there's issues around periodicity. So basically the recurring nature of these payments. We need to have this ongoing transactional relationship. And so some of the problems that we started looking into with this was the pre-authorization. That pre-authorization, cryptocurrencies lack any semblance of pre-authorized payments by design. So this is definitely something that we have to solve. And then and ideally pre-authorization, and also pre-authorization is bad because we ideally want to keep the power in the hands of the users, and this is why cryptocurrency doesn't work like that. As for data standards, the cryptocurrencies share no common language or protocol, and that's why some people are talking about like cross-chain transactions and ways to have that. But especially true in this case, there's no notion of billing period, due date, grace period, late penalty, and stuff that you would see in other subscription systems. And using cryptocurrencies for subscriptions imposes an additional financial risk on customers and merchants about price volatility right now. So we thought, how can we control for these issues in designing something? And so looking at what we needed to actually design, we looked at the required events for it. So subscription service has to have sign up by the customers, they have to do the creation, and they need to check the payment status. There needs to be a way also could be confirming that the payments have been made and communicating that next payment, so that reoccurrence of the payments is what needs to be there too. And this is what we thought is the list, is the MVP, like the minimum viable product to have any kind of protocol that would help for reoccurring private payments. So these. So this is a diagram that we came up with about the sequence of events that has to happen, you know, looking at those things that have to happen, and these are the parties involved. And so we have the customer, the client, in our case is GridSync, but this could be a client on the machine. I think you guys can probably read that it says customer device and external systems. And then the wallet that you need to have to utilize Zcash in this case, and the secure network Tor, and then the merchant would be us, and the payment network, again, of Zcash. And so this is basically the steps that have to come, and the first part is not so, it's kind of interesting, but it's how we really make sure that this loop at the bottom happens without revealing any information that could, that any data that could be used to see any patterns which then could tell you who the person was. Because we have other data, and so if we could correlate that data, we could start to figure out who somebody was, and we don't want to do that. So we need to make sure we do this in a way that's anonymous along the way. So yeah, so I'll go through it in some more detail. So you would visit the Tor-based webpage, and this is where the user would go and say, yep, I want to sign up, and they generate a code for themselves. And this page doesn't have to be very fancy, it really just has to generate the code. And then the code is sent back to them. And then they put the code into their client, and that code then talks to least authority, and least authority's server says, okay, great, you need configuration information to connect to our network so that you can store your data. So we send that Tahoe config and the first signed invoice back to them. And so I'll talk in the next slide about what that invoice contains, but that's the data pieces that we need to add to these transactions to know about how the subscription is going to function, and how it's going to, like the period of time and stuff. And then they make and also we want to sign it for security purposes too. And so we send that signature over initially. And so then they make the payment to a receiving address, which we have put in this initial send of data to their client. And so they know that they need to go to their Zcash wallet and make the payment, and that goes onto the Zcash network, where we're monitoring the Zcash the blockchain, the network, for that payment to appear. And when we see that payment appear, then that's the key for us to generate the next invoice for them. And we basically just update this invoice information to reflect the next state. So your next payment due, basically. And that could be like any period that is defined with the data. And this we serve on and in this design we said, okay, we can serve it on a Tor-based web page, because this way we don't know who they are when they go visit the web page. Because if we put it on our website or any kind of centralized place, we could get their IP address, so then we could find out who they are. There's other problems too. So we thought this way we don't know who they are. And so they just go to this address and they get the data that they need from us. And so, yeah, their client then knows to check for the invoice information on this page, and then maybe serve it back to them in a nice UI or something. Yeah, so it notifies the customer of this invoice information, and that's on the client side, so that periodicity that's happening is on their device, as opposed to out in the blockchain or in some centralized repository where it could be mined. And so, yeah, then they make the next payment when they're ready. And then this can be adjusted. So this is where we're thinking right now of how this could be designed and how this could work. And we know that some of this could be done a little bit differently, but this is something that we could actually build in the next few months. Actually quicker than that. It's not a whole lot of work to do this, but figuring out how it works all together is the hard part. So this is the invoice data that I mentioned. It needs to include a version number, also payment address to receive funds, so this would be the Z address that people need to pay us at, and then the human-facing subscription description, just so they know what they're paying for. Subscription provider public key. This is so that they know that we are who we say we are and that they're paying the right people. And then the payment details, and this is about the subscription. So the time period of the subscription, the price per that time period, the maximum number of payments acceptable, so if they want to pay ahead, and then also payment due date and time. And this is what we think is the minimum data that we would need in order to process this. So earlier you saw some other stuff. Again, we want to preserve privacy, and we want to implement something that has a protocol that enables the customer to pay for subscriptions without intentionally or accidentally disclosing additional information to us or unnecessary and personally identifiable data to either us, the merchant, or any third party, such as email providers, banking institutions, or anybody else watching the network. So every event in our sequence is an opportunity for data to be gathered and be connected back to who we are. And so we wanted to make sure that every event that was happening, that there was some privacy preserving features there. And so Tor for anonymous web browsing, this allows the subscriptions to be discovered without revealing the user's identity via browsing. And To note, this could also be replaced with other secure and anonymous options, but this is what we chose to use right now just because for an initial implementation is because it works now. But I'm sure there's people designing really cool other things out there that we could substitute for this, but we just want to have that privacy feature. And then the Zcash shielded transactions to avoid disclosing transactional data on the blockchain. And again, you could probably re-implement this with another blockchain that had privacy protecting features. Yeah, we just say that when swapping these pieces out, that we would need to reevaluate the whole privacy implications and the security risks of the whole system. So a quick mention for related work. There's Bitcoin VIP 70, which talks about subscriptions, but not reoccurring ones. And this is not an exhaustive list of related efforts, but I just wanted to put that out there in case anybody wanted to look at some of these related efforts. And there's probably some that I missed too. And then there's Ethereum. There's some discussion around subscriptions there too. And there's things like Lightning Network and Bolt for Zcash. And these all are things, different efforts that people are making in the subscription space, but not necessarily with so many privacy features. So our next steps are to implement this on S4 for ourselves, and along with the sapling release, which will make things faster. And then this will give us an end-to-end privacy solution for our file storage system and the payments that people make to us. In this end, this isn't the end solution for us. We surely could build cooler stuff, but we just saw this as like, how could we prototype something really fast, and how could we design just the basics, and we could build really cool, much more interesting things on top of it, but we wanted something functioning as soon as possible. And yeah, we would like to facilitate the development of higher level applications like user-facing wallets, merchant-facing payment frameworks, and stuff that utilize private periodic payments also. So my calls to action for you guys is to contribute to the development of this type of work, talk about the work and raise awareness, implement it, steal our ideas, send us your ideas, send us your thoughts and feedback, and see how far we can take these kinds of concepts forward to have end-to-end privacy for people, not just privacy in pieces. And I have to give credit to the creators of Tahoe Laughs and the creators of P4. It wasn't just me. So, I'm done. I guess, questions, sure?
Do you guys have any questions about P4? If you don't, then I would say maybe we just take a moment. I think it's not quite time for you yet, eh? Okay, so we'll be back in a second with Chris Goes. Cool, thanks. I think we're just going to continue. It's a little bit early, but I think Christopher, is it Chris or Christopher?
Either or.
Chris has a presentation that I think is going to be able to fill the slot anyway. So yeah, do you want to come up and talk about IBC and public-private blockchain interoperation? Just reading off your screen there.
There, this should just work.
And I'm going to grab the laptop there underneath yours as well.
It just worked.
Perfect. There you go. Grab this if you want the...
This will switch to possibly... There we go. Sweet.
Sure?
Yes,
Nice.
it does. Afternoon. My name is Christopher Goes. I work for Cosmos and also Cryptium Labs, and I will be talking about inter-blockchain communication, or IBC, and how we might be able to use it to enable public-private blockchain interoperation. So, a little bit about this talk. First, to lay the groundwork, IBC and Cosmos get conflated a little bit, which is partially our fault, but IBC is a protocol. So it's separate from a particular implementation, a particular network. Anyone can implement IBC in their blockchain state machine and communicate, as I'll explain in a bit, with other blockchains implementing compatible IBC. I'll go over our design goals in constructing the IBC protocol. Hopefully manage to explain a rapid version of how to do it yourself on your own blockchain. And finally, walk through an example of using the inter-blockchain communication protocol to connect the Ethereum and Zcash blockchains to allow you, if you hold any ERC20 tokens, to send those ERC20 tokens through IBC over to Zcash, spend them privately using the Zcash zk-snark circuit, and then perhaps later, perhaps not, send them back to Ethereum, where they would convert into the original ERC20. But before we get to that fun demo, I'm going to tell you how it works. So, what? Inter-blockchain communication. Inter-blockchain communication is a mechanism, first and foremost, for relaying data packets between two chains, which we'll call A and B. Off-chain relayers, so perhaps a server in the cloud, on your desktop, it doesn't matter, are responsible for watching the first chain, chain A, and committing IBC packets, which are sent, so published to chain A in a cryptographically verifiable way, sent to chain B. When published to chain A, they contain some destination data, which will allow these relayers to figure out which chain B they should publish the packets to, and therefore route the packets correctly. I'll get to that in a bit. These relayers, importantly, are not permissioned. So there are different kinds of fee models you can implement on top of IBC to properly incentivize everybody. A very simple option is simply that the person sending the sequence of transactions, sending the asset over inter-blockchain communication, pays the fee to relay, relays themselves. Other options include fee payment in the sending transaction that goes back to the relayer, so that maybe a central group of relayers could relay very efficiently. The IBC protocol is payload opaque. So just like, say, the TCP/IP stack does not define the data payload for the layer on top of it, IBC only defines ordering semantics and sort of correctness semantics for packet delivery. It does not define what the application does. So any kind of application invariance you might want to implement on top of IBC, you can do so. And you can implement these invariants because IBC messages are authenticated. So it's not just that we're sending data from one chain to another. That would be useful, but much more useful is the ability to provide guarantees across the combined state of two chains, or maybe even n chains. So we have some rule set, right? We have a rule set on the second chain, chain B, and that rule set defines a subset of packets, published packets from chain A to chain B, which chain B will accept. We can make whatever rule set we want, and the IBC protocol defines a rule set, which will be executed in the state machine of chain B, that gives us a lot of really useful guarantees, which I'll get to in a bit. But at the very high level, we know that if a packet has been received on B, so IBC relayer committed a transaction on the second blockchain B, and that transaction succeeded, then we know something about the state of A. On chain B, we have some guarantee that chain A, when this packet was sent, had some state, because chain B verifies a proof. You want some way for the state machine, so independent of any trusted relayer, no trusted user, only the state machine of chain B is required to verify the proof that this packet was sent on chain A. There are different ways you could verify that proof. The way we're planning to implement it initially, not quite a Bitcoin-style-like client, but if you're familiar with the Bitcoin-like client model, it's pretty similar, where you have Merkle state proofs for substate. So the IBC packet will contain a proof that it was successfully published on chain A, and then when chain B receives the transaction which attempts to send that packet to chain B will check that proof, check the Merkle path, and assert that it was in fact included in a trusted header of chain A. Another way of doing this, which I'll touch upon later, would be an intermediary peg zone. So sometimes you might not have the option to change the state machine of chain B. If you're working with a capable contracting language on top of a VM like the EVM, you definitely can. But if you want to utilize IBC with an existing chain where you can't change the state machine at all, like Bitcoin or Zcash, or perhaps a chain where you just have less control, you might want to use something called a peg zone. So what must you trust for IBC? This is integral. You trust the consensus algorithms and you trust light client verification. Only, but if and only if those two are correct, can you assert all the invariants that IBC will allow you to assert. Use cases. So the basics. As I've alluded to, IBC will allow you to transfer tokens, fungible tokens, non-fungible tokens, possibly other kinds of tokens across multiple chains. You can conditionalize contract execution on Ethereum or transaction output locking, perhaps, on Bitcoin, on the state of another chain. So you could say that some contract on Ethereum can only execute if Bitcoin was sent to such and such address and Zcash was sent to another address. You can conditionalize on the state of multiple chains at once. In some ways, IBC is like sharding. There are many sharding proposals, but it would allow you to split and parallelize the contract logic against multiple chains with compatible virtual machines. So you could shard the code of your contract onto different chains. IBC exposes a channel-like primitive. If you've ever worked with Golang or another language which exposes a channel on which you can send and receive and which sort of blocks, or so to speak, you could write contracts using channels that would translate into lower-level IBC calls. You can compose hybrid state machines with different VMs, so you can't really shard a contract against different VMs, but you can still have a sort of virtual contract on top of multiple chains, which ends up using different underlying state machines, so EVM, Cosmos, and Zcash, for example. Another example use case we're really interested in is delegated security. So since IBC provides proofs of actions on one chain to another, you could use IBC with multiple proof of stake chains to delegate the security of one chain to another. What does that mean? That means that if a validator commits a protocol fault, an attributable protocol fault on one chain, then that chain sends an IBC packet over to the other chain, maybe a chain with more value at stake, or a chain where all the validators sort of agree to use as a consensus point, and the validator can be slashable on that chain. So even if the chain which you're sort of running your VM on maybe doesn't have as much value at stake or doesn't have as much security, if you can get your validators to agree to accept being slashable on another chain, that process can be conducted in a verifiable way over IBC. So the key point is that IBC allows for heterogeneous chains. It's not a sharding proposal to split the same chain into multiple pieces and parallelize execution that way. It's a sharding proposal to split any number of chains into any number of pieces and parallelize or don't parallelize whatever you want. And the advantage of that, we think, is that sovereign chains can have really custom and maybe really risky features, right? Bitcoin didn't want to add zero knowledge proofs because they were kind of untested crypto, which is a reasonable concern. You don't want to put the Bitcoin network at risk. You don't want infinite inflation if the trusted setup was compromised. But this way, with IBC, you can elect to send your assets to the chains which have the features you want to use, make use of them there, send them back or not, and choose which risk profile you want to accept. So how does this work more concretely with implementing what we'll say is a cross-chain contract or a model across multiple chains at once? You want to be able to preserve invariance, contract invariance, across the combined state of several chains. So let's say you have a fungible token, which is defined by any number of units of that token being exchanged for any same number of units. It's fungible, and a finite total supply. So you can't mint tokens out of thin air, and you can't, maybe you can delete them, but you can't delete them for the simple example. How would you do that over IBC? So the IBC send packet on chain A would burn the asset or escrow it, perhaps. So if you want to send an ERC20 token, you would have a contract on Ethereum, and you would send your tokens to that contract, which would then escrow them in the contract until later. and it would provide an IBC send proof that those tokens had been escrowed. Then on chain B, when the IBC packet is received, you can mint what we'll call T vouchers. So T vouchers are another token. They're a native token of chain B, which could have like a different rule set, although it needs to have the same basic fungibility guarantees. And then later on, when you're done with chain B, you've done whatever you want to do there, you can burn the T vouchers on chain B and redeem the previously escrowed T tokens back on chain A. So one interesting question here is, which is really the voucher? IBC does not natively have, as a protocol, one canonical chain or any canonical chain. So is it the asset T on chain A? Is it the T vouchers on chain B? Which was original? Nobody knows. The state machine of B, of course, must verify that the state machine of A actually burned these tokens. So there are different ways to do this. The way we will implement initially, in sort of the Cosmos IBC implementation, will encapsulate most of this knowledge in the state machines themselves, right? So when we write an IBC connection on chain B, we will know that the IBC send can send a state machine on chain A, execute such and such logic, and we'll know that it burns the tokens. That is a little limited in that it precludes implementing connections in certain orders, because you have to know that beforehand. You have to know that when you're implementing the IBC connection on chain B, what type of packet corresponds to burning T tokens on chain A. Other future options for less limited versions would involve some degree of compatible VMs where you could verify the code itself. So if the code, as it is in Ethereum, is accessible in state, and you can prove that some certain code is at some certain address, then you could have more dynamic connection and reconnection logic. So after A burns T, in either case, when sending the IBC packet, A writes some data to a provable store, Merkle store most likely. And then B can verify the light client proof of the written data. I'll get to exactly what the data is in a second, but the important part is that the data couldn't have been written if T hadn't been burned, right? That's the guarantee you want on chain B. You want to preserve the total supply across both chains, and to do that, you need to know that when you're minting these vouchers on chain B, you burn the vouchers on chain A. Okay, so IBC implementation, concept one, connection. Connection is the set of data stored in consensus state necessary to verify packets between two chains. So to open a connection between two chains, you need to start with what we call a root of trust. A root of trust could be a genesis block, an initial validator set at connection creation. That needs to be defined when whatever you're using to implement the IBC connection is deployed, which might be a smart contract, which might be a governance software upgrade, which might be something else. Any connection user, notably, can check the root of trust, so someone has to decide what it is, but anyone else who actually uses this connection can verify that it is what they expect. Then you want to, once you start with your connection, update headers. So to verify Merkle proofs in subsequent blocks of packets that have just been sent, you need new headers from the source chain to verify that the packets have been proved in state. So you need some function which allows you to verify an update from header set 1 to header set 2. With Tendermint, this function tracks the validator set and checks that 67% of stake has signed the next validator set hash. Subsequently, there's some fancy bisection ways to make that faster if you have infrequent IBC packets. But the essence is simply that you check that each governing stake of the proof of stake network has signed the next update, then you know to trust the next header. In Nakamoto consensus, the previous chain continues with most work seen as long as it extends that sequence of blocks. Headers, allow for packet proof verification, as I mentioned. So closing a connection. Usually you don't need to close an IBC connection. It can remain open forever. And if you want to continue sending packets between those two chains, there's no need to open a new one. However, in exceptional cases, you might need to do so. If there were a fork, depending on whether the connected chain was proof of work or proof of stake, this varies. Or if there were a safety violation where some chain committed a protocol fault, maybe, signed two valid histories in the case of proof of stake, what and how this must be done depends on the kind of Byzantine event that occurs. So if it's some identifiable fault, it could be easily done automatically. If two valid headers at the same height for tendermint consensus are both published to the IBC contract, you know that a protocol fault has been committed, and you can close the connection and stop any further packets from being transferred. So on top of a connection, we have messages. And IBC implements a vector clock for two processes, which in our case are blockchains. And then messages can have ordering guarantees over this vector clock. So if we have two chains, A and B, some packet counter I, X and Y events on these two chains, which are other transactions, we know that when if A sends packet I before B receives packet I, B receives packet I before A gets the receipt for packet I, A sends for packet I before A sends for packet I plus 1. And those three things are all guaranteed by the state machines we implement IBC in, right? So we implement that queue logic, which I'll get to in a second. Then we know that if X is before A send packet I, X will be before B has received packet I, and if Y is before B has received packet I, Y will be before A gets the receipt for packet I. And you can see that we can provide like counterfactual proofs for how total supply is conserved this way. This is generalizable, although we probably won't do it initially, but it's generalizable to an end process vector clock if you want to order events between multiple chains, so that you might all construct a packet sequence so that you would always know that event A on chain A happens before B on chain B happens before little c on chain C. So the ordering guarantee can be used to reason about the combined state of both chains as a whole. With the example of fungible token total supply, if packet I is sent on chain A, then we burn the tokens. If packet I is received on chain B, we mint the vouchers. And we know, because of that counterfactual there, we know that the tokens must have previously been burned on A, so total supply is conserved. Counters and metadata are used to prevent replay. So replay is a concern with IBC because these packets are just data, right? You send you send a transaction to chain A, which provides an outgoing proof for packet I to chain B, and then that proof is some data. So we only want that proof to be usable once on chain B and chain B only, and we want chain B to know that it came from chain A. How do we do that? We have 4 queues. So each chain for each chain A has 2 queues, one for outgoing packets from A to B, each storing the packet information, so it can be proved with a Merkle path, including a sequence counter, and an incoming queue for receipts for sent from B to A to acknowledge outgoing packets. Chain B has the reverse set of queues, outgoing packets from chain B to chain A, and incoming receipts from chain A to chain B. Each queue keeps a counter, and packets can only be sent and received in order. So the state machines on chain A and chain B check that if I'm receiving packet I on chain B, that I've already received packet I minus 1, and I won't accept packet I plus 1 until I've seen packet I. Each IBC packet is a 5-tuple, including a type. So this is used from multiplexing, which isn't important for understanding the protocol, but it easily allows you to reuse a single connection with multiple applications. A sequence, which is the ordering guarantee to prevent replay of the same packet on the same source and destination chain. The source chain, which is to prevent masquerading, so you don't want it to be the case that I could pretend to be sending a packet from chain C to chain B when in fact the packet came from chain A. The destination, which prevents the same thing, except for replaying on another chain where you masquerade a packet which was intended for B, but instead attempts to confirm it on chain C instead. And data, which is the opaque application-specific payload. So these, combined with the queues, give you the guarantee that packets are committed once, exactly once, in order from only one chain to only one chain. Receipts, acknowledgements, and timeouts. So an IBC receipt is an IBC packet back to the source chain, which proves that the original packet was received and acted upon, right? So what that means depends on your application. In the case of the simple fungible token example, it means that some vouchers were minted on chain B. And then once chain A gets that IBC receipt back, the receipt is just a standard packet. We call it a receipt to distinguish its use case. Once chain A gets that receipt back, it can delete the data for the Merkle proof, and it can also do some safety things with regards to asset escrow, which I'll get to later. The IBC timeout on the source chain will allow you to specify in an IBC packet as an additional field, so this is optional, a timeout T, which can be specified as a block height or as a timestamp, if you have a consensus timestamp, relative to the destination chain state, so in the state of chain B. The destination chain, if you want to implement this safely, needs to reject packets past T. T must be proved back to the source chain if you want to be able to release assets. So one concern with IBC is what happens if chain B is censored or offline, or the transaction fees are super high, or for some reason you can't get the receipt packet, the destination packet confirmed on B. And timestamp allows you to guarantee that if that doesn't happen, you can still get like a header proof from chain B that the timestamp was past something and that this packet hasn't actually ever been confirmed, and then you could re-release the tokens you escrowed on chain A and try again. Why? What does IBC give you? First, it gives you one asset, many chains. Assets can be freely transferred. Send your Bitcoin from Bitcoin to Ethereum to Cosmos to Zcash, then back or not. It's always the same at Bitcoin. We're not creating new assets here. Through that path, going back through Zcash, through Cosmos, through Ethereum, and then back to Bitcoin, you can always get your vanilla Bitcoin back, assuming all those chains are working as usual. Or maybe even through another path, if people are willing to exchange IBC assets created through a slightly different path, which we expect to happen. Multi-hop routing can reduce the implementation cost, since as long as the sort of the APIs between different blockchains implementing some subset of IBC, like IBC for fungible tokens, are the same, then you can route your IBC packet through blockchains which implement connections to the other chains you want to get to, as long as the path exists. And it's permissionless. You can set up a chain, implement IBC with an existing asset, and add new features without asking anyone's permission, which we think is an important characteristic. New features, old security. When you need privacy, send your Bitcoin to Zcash. If you want maximum security, keep it on the Bitcoin chain. You need to be a little careful if you're doing this kind of transactional style IBC about linkability. Zcash has a great blog post on this. The linkability of something like transparent shielded over IBC is basically the same as the linkability of transparent shielded just on the Zcash chain. So when you send your assets to Zcash, which is the example I'll get to in a sec, they initially start out as transparent, and then you can shield them and transact them as shielded, but when you send them back over IBC, they become transparent again. Doing it this way, using the Zcash example, there's no trusted setup risk, because the IBC contract on the Bitcoin or on the PEG zone can track the total supply in or out every time a packet is sent or received, which escrows or unescrows tokens. And so you know, as long as you if you don't trust the trusted setup, if your Bitcoin is on the Bitcoin chain, you don't need to accept the risk of inflation, but anyone who trusts the trusted setup can elect to send their Bitcoin to Zcash and accept that risk. Risk is always opt-in. These guarantees are generalizable for most kinds of assets you would want to transact over IBC and also other more complex contracts. Opt-in upgrades. This is one thing I am most excited about. There are lots of really interesting governance proposals coming out. Few of them so far feature minority protections, but there is a way, or an interesting possibility of a way, to do chain upgrades over IBC, or some part of the IBC protocol, which would not require governance and which would provide full minority protections. So, to do this, you would copy, let's say I want to change Bitcoin. I would copy the Bitcoin chain, I would add some new features, and create an IBC connection back to the old chain. I wouldn't make a new asset, but anyone could elect to move, and perhaps this is Bitcoin to Bitcoin through a Cosmos zone, move their existing assets to the new chain, if they wanted to, or they could keep them on the old chain. Security-wise, that's the concern, right, is security. So what if the new chain isn't mined by a lot of people or doesn't have a lot of value at stake? With simple proof of stake, it's just less secure initially, and you accept that risk. But it will be more secure as the staking token moves from the original chain to the upgraded chain. With delegated security, as I mentioned earlier, since the new chains, if the new chain's validators accept being slashable on the old chain over IBC, then you get the same security because the same value is at stake in proof of stake. No need for a new asset, and both chains can peacefully coexist. If half the stake of a proof of stake chain, slowly moves over to the new chain of IBC, you end up with two proof of stake chains which can continue on their merry way. Consensus requirements. Let me quickly check time. Okay, I'm okay. Consensus requirement, state finality. IBC safety requires finality, otherwise coins could be double spent. So where in the consensus landscape can we work this in? Tendermint and similar PBFT have instant finality, so as soon as a block is confirmed, we know it's final. We can send an IBC packet. Casper FFG has fast finality. Nakamoto consensus, into which I would class proof of work, and Tezos, and the latest proposal of Ouroboros Preos that I've read, proof of stake, have probabilistic finality. So you need to pick a threshold and a number of blocks after which you accept a transaction, and thus an IBC packet is final. You can vary this threshold if you want to based on the transfer amount, which might correspond to risk in your threat model. Proof verification, which is a state machine concern. With smart contracts, with a custom state machine, you can do this natively. So you can implement all this IBC logic in your state machine. But if you want to use an existing chain without smart contracts, you might need to use a peg zone. What is a peg zone? So a peg zone is something called an accountable federated peg. Federated pegs were kind of all the rage a few years ago, and then they seem to have fallen out of fashion. But the main difference between what we conceive of as a peg zone and some of the previous proposals is that all of the peg zone validators are accountable and slashable if they do anything wrong. So to do this, we need a multi-signature, which could be weighted or K of M, depending on the chain. On the peg chain, you want to join with the zone, so on Bitcoin or on Zcash. In the future, this might be a multi-party ECDSA protocol, which has some nice advantages, but those are not quite production ready yet. Then you have a second Tendermint chain, which has the same validator set as the multi-signature account. So transactions which are committed to the second Tendermint chain must be signed by the multi-signature and then can be relayed to the main chain to Bitcoin or to Zcash. Transactions which were signed but not committed to the bridge are attributable and are slashable, or transactions which were not committed but were signed are also attributable and slashable. And depending on the multi-signature update, if you have a K of M or weighted, it's a little different, but you could also slash for failure to update the multi-signature if the validator set has changed. And because there aren't as many concerns about slashing in cases when a transaction has to be confirmed, because the people you're slashing are also the validator set of the chain, so it's not in their incentive to censor themselves. And you can configure on this peg zone how many confirmations you treat as confirmed for the purpose of IBC proofs to other chains. So an example, how you would use this to join the Ethereum, use IBC to join the Ethereum chains and the Zcash chains to convert your ERC20 tokens to and from Zcash user-issued tokens. What are Zcash user-issued tokens? Zcash user-issued tokens are a super cool proposal, and hopefully someone from Zcash here can correct me if I get anything wrong, but I did read the latest version of the issue, which would implement Bitcoin-style colored coins on Zcash. Or something very similar. This is not in Sapling, sadly, but hopefully will come pretty soon, and alternatives to this exact example you could implement without a new circuit would be a Zcash fork per ERC20 token, which exists just for that token, or implementing Zcash, the asset, as an ERC20 contract on Ethereum. How do you do this? So first, you need to choose how to associate each ERC20 token contract with a unique UIT identifier, which we presume to be some string. An easy way to do that is IBC/Ethereum/contract address. And that way of doing it has the advantage that you can create this identifier lazily on demand. So you can implement this whole system without knowing which tokens you're doing it for. You can just do it for Ethereum tokens generally, and then later on add whatever tokens or new tokens which are created after you implement implement the peg. This will allow you to take ERC20 token vouchers on the Zcash chain, which are user-issued tokens, and do anything you would do with a user-issued token on the Zcash chain. They can remain shielded, they can be shielded transferred, you get the full privacy properties of the Zcash circuit. But then, if you want to take them back to Ethereum, maybe there's some Ethereum-specific ERC20 interaction with another contract on the EVM, you can convert them over IBC back to the original ERC20 tokens and do so. What components do you need to implement this? You need a dedicated smart contract on Ethereum that holds the ERC20 tokens in escrow when people deposit them in order to redeem the vouchers on Zcash. That contract provides the proofs that we talked about earlier, the proof necessary for the IBC packet, that some amount X of some token Y has been escrowed on Ethereum. Then in the peg, the peg zone, you verify proof that the user-issued token has been burned, and you release the escrowed ERC20 tokens on Ethereum when you send the UITs back from Zcash. So some of the channel ordering semantics I talked about earlier are optional. IBC is a pretty modular protocol. You can take the pieces you need and leave the pieces you don't. And in the case of transfers, you don't need quite so much ordering. It's fine if they're commutative. So the Zcash multi-signature peg chain is responsible for maintaining a multi-sig account on Zcash, and then the signer set of the multi-signature account signs the Tendermint chain, commits blocks, verifies the proofs, and any of the validators on this chain agree to be slashable if they commit an attributable fault, signing the run transaction, failing to obey whatever is written to the peg chain. So step one, if I'm a user wanting to convert my ERC20 tokens into Zcash user-issued tokens, what do? I send my ERC20 token, we'll call that T, on the Ethereum chain via the usual transfer call to the IBC smart contract. Then the IBC contract escrows that ERC20 token and logs that escrow event in Ethereum state tree, including all the requisite information to mint the vouchers on the Zcash chain. So the sender, the token, the amount, the destination address, or public key. On the Zcash peg chain, what happens? We get this IBC packet. So this IBC packet started by this transaction being sent on Ethereum. Then a relayer has copied the proof of that transaction, the event log, over to the Zcash peg chain, a transaction on the peg chain. Then the Zcash peg chain verifies that proof. Once the Zcash peg chain has verified the proof, the multi-signature account signs a transaction which mints the user-issued tokens on Zcash in the amount that was proved in the original packet to whatever destination public key was provided. And then that person who had provided the public key, which could be the original user or not, can receive the user-issued tokens, spend them as normal, go pay some people, pay perhaps for least authority storage, as was presented earlier. Then, once they're done doing that, if they're ever done doing that, they can send them back to Ethereum in reverse. So burn the UIT on Zcash, which will need to be made transparent first, but that doesn't have any privacy implications because you have to do it to send it back over IBC anyways. Burn the UIT on Zcash, submit the proof to the Zcash peg chain, and then the IBC relayer will submit the proof of the burned UIT to the Ethereum smart contract, which will unescrow the tokens, and you now have them back on Ethereum. What are the properties of this model? It is permissionless, it's opt-in. Anyone can implement it for any token. Which chain to keep your assets on, and when to move them is up to the asset holder. No risk for the existing ERC20 token, in this case, holders, since the contract total supply. When the UITs are shielded on Zcash, you get the full Zcash level privacy. Same level of linkability as the transaction addresses and the unshielded as transparent addresses when you send over IBC, so you have to be careful about that. But the implementation is also scalable. The same logic, one peg chain can handle probably all of the ERC20 token contracts that will ever be in existence. And Tendermint will always be a faster consensus algorithm. Future research. Again, let me check time. Okay, I'm going to speed through this. I'm going to take questions. So, any questions? Yes?
Can you talk about 51% attacks on a peg chain?
51% attacks on a peg chain. So, proof of work peg chain or a proof of stake peg chain?
Proof of stake.
Proof of stake peg chain. So usually in at least in Tendermint proof of stake, the threshold is not 51%, it's 34% to halt or 67% to control. And I'll just go back to my other slide. So what if consensus breaks? There are a few different ways in this could happen. You could end up, so IBC cares about some notion of valid, and valid isn't maybe your notion of valid, but IBC's notion of valid is a chain that can provide like client proofs that verify. So in different Byzantine scenarios, you might get no valid chain, or you might get invalid chains. If the stake splits 50-50 on a proof of stake chain, you will get no valid chains. So no progress can be made. If you used IBC timeouts on the source chain, then any packets were in progress, you can recover the assets for, but you'll end up with an asset split across two chains, right? So you'll have some ERC20 tokens on Ethereum, and some vouchers on Zcash. Right now, you just accept that risk. It would be possible to implement some kinds of fraud proofs, but that does impose pretty complex requirements on the state machines of both chains because they have to verify much more about each other. Governance on one chain, if the chain has governance, could apply an irregular state upgrade and credit tokens at parity with balances on the other chain, right? So if the first proof of stake chain has governance, the second one halts, the first one governance could elect to mint the tokens back for the holders of the peg token on the second chain. But that's not the ideal case. So we're still working on this. Does that answer your question? Other questions?
No other questions? All right, big round of applause then.
Thanks. So you can find the spec at that link. I'll post the slides. My email is cwgoas@tendermint.com. And I encourage you to check out the breakout on zero-knowledge state transitions, 1540 in breakout room 2 to continue discussion in this vein. Thank you.
See you soon. Off.
Well, so I was telling you, I started listening from the beginning and then like jumped to more recent.
Oh, thank God you jumped. It got so much better. We are like,
You're like legit now.
we're legit now, and it's we should. I mean, we leave it, which I think is okay to do, but it's also a bit of a like it's leaving your amateur. And like there are people that like you start from the beginning thinking like people have said this is like a decent podcast. You're like, why are they talking about breast fest? Like.
Yeah, that
Joking about bullshit. Like, that's our first episode, super bad. But I guess it gets better. So I'm gonna go really grab a drink and then I can just go ahead and just.
Yeah, we did retreat in December.
There might be a few people coming in right at the end. We'll close the door at some point, but there's a group that I know.
Okay, hey everyone. My name's Noah Johnson. I'm going to talk about privacy-preserving smart contracts. So a bit about myself. I'm a PhD student at UC Berkeley, and also co-founder and chief product officer at Oasis Labs, which is a company building a smart contract platform based on some of the research I'm going to talk about today. So let's start with a brief history of blockchain. So, of course, blockchain became popular in 2009 with the introduction of Bitcoin. Later, Ethereum came along and introduced the concept of smart contracts and showed how to run general-purpose computations in a distributed way. And then recently, we've seen the rise of new sorts of applications, including games, like CryptoKitties. CryptoKitties is interesting because it's the first blockchain application that really went mainstream. Unfortunately, CryptoKitties also exposed cracks in our current infrastructure. When CryptoKitties was popular last December, it caused major congestion in Ethereum. It caused transaction costs to go through the roof. So this is where we are today, and there's a question of, what do we have to look forward to in the future? If you're bullish about blockchain, which I hope everyone here is, then you'll agree that in the future, blockchain will power a set of applications that are significantly more complex than CryptoKitties and anything that we've seen so far. These are applications that people get excited about when they talk about blockchain and its revolutionary potential. Things like credit scoring, medical diagnostics, private auctions, and so forth. And so my talk today is going to focus on what are some of the challenges for supporting these applications and what are requirements of the underlying infrastructure in order to address some of those challenges. Just a quick teaser, you'll notice here that all of these applications require a lot of computation and they all require a lot of data, and oftentimes the data is sensitive. So let's start with a concrete example to sort of motivate the challenges. This is a credit scoring application. So in this application, you have a number of institutions that contribute their data into a smart contract, which is designed to train a machine learning model with that data. And of course, this runs on workers or miners that are part of the underlying platform. And the smart contract might output, a model from this training data. There are variations of this. Maybe the model would be stored inside the smart contract and the smart contract would expose a way to query the model, but the challenges are the same either way. So this is great. It's a great use of blockchain in that all of these institutions know that if they do this with a smart contract, the data will only be used for the purpose of training this credit scoring model. And users who may want to apply for a loan based on this model have visibility into how their data is used and how the model is trained. So this is ideal. Unfortunately, if you tried to build something like this on today's platforms, you would face a number of issues that essentially make these sorts of applications a non-starter. The first issue is that, of course, the data is very sensitive, and so there's nothing stopping workers that actually run the smart contract from stealing the data. Even if you trust the workers not to steal the data, there's also this risk that when you're training a machine learning model on sensitive data, the output model itself might leak information about the inputs. Now you might think, well, clearly a machine learning model is, already private, right? And hopefully by the end of this talk, I'll convince you that that's not the case. And then the final challenge, of course, is that today's blockchains just fundamentally aren't designed to scale to complex workloads like machine learning. Already, we saw CryptoKitties. Even though the breeding algorithm in CryptoKitties is not that complex, even something like that, significantly slowed down the entire Ethereum network. So fundamentally, those platforms are not going to be able to accommodate these sorts of more advanced use cases. So each of these problems actually requires a solution at different layers of the stack. And so I'll talk about solutions for each of these. At the layer of the workers, that is the risk of the machines that run the smart contract leaking sensitive data, we have a technique called confidentiality preserving smart contract execution. At the layer of the application, and specifically the risk of data leakage through the result of the computation, we have a class of techniques called privacy preserving analytics and machine learning. And then finally, at the infrastructure level, we have some new design that allows for more scalable smart contract execution for significantly more complex types of smart contracts, not just simple transactions, which is the focus of much of the work in this space. So Right, so this requires a top-to-bottom approach, from the application layer all the way down to the infrastructure, and we'll see to the hardware layer. In this talk, I'm not going to talk about scalability. This is, of course, a hot topic in this space. There are a lot of projects that are looking at how to build more scalable platforms. Given this is the Zero Knowledge Summit, I'm going to focus on the privacy-related problems. So I'll talk about confidentiality and privacy. So the first one, confidentiality preserving smart contracts. So the basic abstraction of a smart contract, of course, it's a piece of code that takes some input and the current state, and it runs the code on that input and outputs a new state, which is recorded back to the ledger. The abstraction of a confidentiality preserving smart contract is that all of these inputs and outputs are encrypted. That means that nobody can see the data, not even the workers that are executing the smart contract. Now, given that no one can see the inputs and outputs, it's essential that the system provides a way for the workers to prove that the execution result is correct. And we saw how this works, for example, for zero-knowledge proofs, where essentially zero knowledge allows you to run all of the computation locally and only output this proof. But the more general version of this problem is you have some piece of code, the data is sensitive, you can't rerun the computation locally yourself to convince yourself that the result is correct, right? Because the data is secret. And so we need schemes that allow proving that the result is correct, even if you can't see the underlying data. So it turns out there are a number of different technologies that can be used to implement confidentiality preserving smart contracts. And these can be kind of broadly categorized into hardware-based approaches and crypto-based approaches. So the challenges of these cryptographic approaches like multi-party computation, zero-knowledge proofs, and homomorphic encryption is that they tend to be very slow. They incur often orders of magnitude performance overhead compared with native computation. And so one of the research goals for our platform is actually to combine these different techniques together to allow the developer to choose which application makes sense, because each one has different trade-offs in terms of the performance and the classes of applications that it can support. In this talk, I'll focus specifically on secure hardware because we've heard many discussions on really exciting new work for some of these other techniques. So secure hardware is a technology. There's various implementations of this, but the fundamental abstraction is what's called a trusted execution environment, also known as an enclave. And an enclave essentially is a piece of technology that allows an application to run in a protected way. So an enclave provides two important security properties. The first one is that it guarantees that the operating system and other applications can't modify or tamper with the execution of the application inside of the enclave. So this is what we call integrity. It means that the computation result is guaranteed to be correct. The second property is confidentiality. So this means, again, that the operating system and the applications, as well as even the user of the machine, can't actually inspect the state of the execution, including the code and the data. And secure enclaves also provide what's called remote attestation, so the hardware can generate a proof, essentially, of the contents of the enclave, where that proof can be verified by a remote party, even if they don't have physical access to the machine, to prove that the right code was running inside the enclave and that the entire thing was running on authentic secure hardware. So essentially, you can think of secure enclaves as a black box that can't be viewed or tampered with, even by the operating system, the hypervisor, and the user of the machine itself. So you might notice actually that this property of integrity, that is guaranteeing that when an application runs on a remote machine, the execution result is correct, actually is very similar to some of the goals of smart contract platforms. It turns out that both of these technologies actually have similar goals. They both try to run a piece of code in a way that achieves certain properties. And they do this in very different and complementary ways. So smart contracts and platforms like Ethereum, of course, they guarantee integrity just by virtue of the consensus protocol that's used. Also, they have strong availability and persistence because they are replicated and decentralized and store state immutably on a distributed ledger. But today's smart contract platforms don't provide any confidentiality. Now, trusted execution environments also provide integrity that's enforced by the hardware. On the other hand, they provide no availability or persistence, right? You can just turn off the machine and you lose all the state that's running. but they do provide confidentiality. So if we can combine these different technologies together, essentially we can get the best of both worlds. And that's exactly what we did in a recent research paper called Ekiden. So this was a collaboration between Berkeley, Cornell, and UIUC. And in this paper, we show how to combine secure hardware with blockchains in order to essentially endow smart contracts with confidentiality. So the key idea is to execute the smart contract itself inside of this secure enclave and then store the state back to blockchain in order to get persistence. So getting this all to work is actually quite a bit more complex than you might think. You need to separate the execution from the consensus because secure enclaves have no internet connectivity. You need to design new cryptographic schemes to prevent replay attacks and rollback attacks. So there's a lot of interesting details. I encourage you to check out the paper if you're curious about that. In this paper, we implement several different applications that show the advantages of being able to keep smart contracts state secret. We also ported an EVM to run inside the enclave so that any existing Ethereum smart contract can immediately benefit from confidentiality. And to demonstrate this, we ran the actual CryptoKitties breeding algorithm inside the enclave. So this is a good example, actually, of the advantage of keeping state secret. The developers of CryptoKitties actually intended to keep the breeding algorithm secret. They obfuscated it and didn't release the source code. But because on Ethereum, of course, even the bytecode is public, then people were able to reverse engineer it and sort of game the system in order to increase their likelihood of breeding valuable cats. So this is really promising. It suggests that trusted hardware could be used as a primitive for secure computing, not just for blockchains, but for general computations. In particular, secure enclaves provide a number of strong security properties, including the ability to authenticate the hardware itself, the ability to authenticate the device, and to guarantee the integrity and privacy of the execution, even for executions that run on remote machines. So this could become a platform for building new security applications. And there's actually several recent research projects that show how to use secure enclaves for cloud computing. These aren't specific for blockchain, but they are solving a very similar problem. And actually all hardware manufacturers, or at least the major hardware manufacturers, recognize the importance of this problem. So they've all shipped versions of secure hardware in their recent chipsets. Most notably and well known is Intel Secure Software Guard extensions, but NVIDIA and AMD have shipped secure hardware as well. Now, not all of these provide the core features I described earlier. For example, AMD's version only guarantees confidentiality. It doesn't guarantee integrity. But this is clearly the direction that the industry is moving. But there are still major challenges. So all of the secure computing techniques I described earlier, including the cryptographic techniques, all have different trade-offs in terms of the adversary model. And this is true of secure hardware as well. So what I described earlier, those properties are, of course, properties of the abstraction. Those are ideal properties of a secure enclave. In practice, of course, there's no such thing as a perfectly secure system. It's a matter of trade-offs. And so there are some open questions of how secure can secure hardware be and under what threat models. An interesting thought experiment is, what would you entrust to run inside one of these secure execution environments? Your Bitcoin keys, your financial data, your health data. You probably are already using some version of trusted hardware if you use a hardware-based wallet, right? And you can see the advantage of having a hardware-based mechanism to protect the sensitive material, in this case your Bitcoin keys, which means that even if your machine is infected with malware, unless someone has physical access to the machine or to the device, they're not able to steal your keys. And so in some sense, secure enclaves are just a generalization of that concept. And of course, you could layer these other secure computing techniques onto secure enclaves to provide additional security. Like you could run multi-party computation inside of an enclave, because multi-party computation has a different threat model that is complementary to secure enclaves. Multi-party computation assumes that multiple parties aren't going to collude and share answers, whereas secure enclaves assume that someone can't physically tamper with and break the key properties of the hardware device. So one of the research directions of Oasis is how can we do even better than what we have today in terms of the security. And so in order to get there, let me list out what we think are the key properties of a secure enclave. The first and most important is that it needs to be an open source design. So everything in the blockchain, everything in the blockchain space, of course, is open source. And so to the extent that you're relying on hardware for any part of the security or integrity of the platform, the hardware itself had better be open source as well. And there are advantages to having the hardware be open source. That means that it's more transparent. It allows other researchers and security experts to audit the design. It's more amenable to formal verification. And so unfortunately, and as well as secure supply chain. So if it's open source and in the public domain, then any chip maker can actually tape out one of these secure hardware chips. And so today's secure hardware technologies actually don't provide this property. But we're working on a project that does. So there's this ongoing project called Keystone, which is a fully open source design for secure hardware. And this is a collaboration between Berkeley and MIT, and they expect an initial release in fall 2018. The Keystone design is based on the RISC-V microarchitecture, which was developed out of Berkeley. And the nice thing about building on top of RISC-V is that it's already widely adopted in industry. And so the plan for this project actually is to have an initial release in the fall that runs on FPGAs, and then a release later, I think early next year, that actually runs on an existing RISC-V chipset. Last week, we actually had a workshop at UC Berkeley that brought together industry and academic leaders in secure enclaves. And the workshop was specifically focused on kind of open challenges in building a fully open source secure enclave. So that was exciting. Okay, so that concludes the first part of my talk, where I talk specifically about techniques for securing the computation. Now, assuming that we've secured the computation so that workers can't leak data, now the natural application for smart contracts is let's do things with sensitive data, because now we have assurances that the workers can't leak data. And so now this brings in a completely different set of challenges related to how do we safely use sensitive data in such a way that smart contracts can do useful things with the data, but we can still guarantee the privacy of the users in the original data sets. And I want to discuss this briefly because I think it's a problem that is still, at least today, less understood in the community. So I'll discuss the challenges in a general way, but hopefully you can see how these apply directly to a lot of the smart contract applications I listed earlier. So to motivate privacy risk, let's suppose we have a data set of trips, right? And on the one hand, we have an analytics question that asks how many people visited New York last year, and on the right we have a question that asks how many trips did Joe take last year. So clearly, the question on the left is safe, right? It doesn't violate anyone's privacy, whereas the question on the right very clearly violates Joe's privacy. Now, these questions are asked of exactly the same data, right? The only difference is specifically what type of question was asked and what information is revealed in the answer to that question. And so there's sort of a broader question here. How do we reason about the difference between these two queries? The fact that this one is sort of intuitively safe and non-privacy violating, and this one very clearly violates privacy. And how do we, these are two extremes, but how do we kind of bridge the gap and reason about something in between? And in addition to kind of formalizing this, there's a question of how do we build a system that can automatically allow things that are safer and protect against things that are less safe? So I want to point out that actually this isn't an access control problem. This is not a problem of just restricting access to certain portions of the data, because again, both of these queries run on exactly the same data set. And again, the only difference is what specific question is asked of the data. So that's privacy risks for statistical queries. You also need to be very careful when training machine learning models on sensitive data. So one example, and there's a paper that illustrates this, is training a deep learning model on some email training data that had social security numbers and credit cards. And this paper showed that actually an adversary can query the output model in order to reconstruct the original input data, credit card numbers and social security numbers, strictly from the model itself. And in other work, people showed how to, if you know properties of one person's data, it's very trivial, given the model, to determine whether that member was part of the original training data or not. And one more example is, here on the right, sorry, the left is an image that was reconstructed from an image classifier model that was trained on an image on the right. Okay, so clearly there are major privacy risks, even for things that seem innocuous, like statistical queries and machine learning on sensitive data. What people have done today, the sort of the state-of-the-art technique for addressing these problems is called data anonymization. And how data anonymization works essentially is scrubbing fields in the data that could reveal individuals. And there are different versions of this. The basic idea is, of course, names could identify people. IDs oftentimes can be linked. So we're going to mask that data. Certain information we might bucket so that it's more coarse, right? So that there are fewer distinct values, and so forth. And so once we've done this process, then this is the data set that would be released for analytics. So this might seem good on the surface, right? We've removed PII. We've masked any information that could be used to identify individuals. Turns out there are actually a few problems with this. The first is that the process of anonymizing data actually skews the results of analytics on the data, even analytics that would otherwise be safe. So for example, if a doctor is training a model for detecting the risk of high blood pressure, if this is what the actual result is, then anonymizing the data set may very well produce a result like this. And the reason for this phenomenon is that the process of anonymizing the data is very blunt, right? It doesn't take into account specifically what's being done on the data. And in an example like this, actually all the users would prefer probably that this particular model was trained on the original data set, right? Because it clearly doesn't harm any of their privacy, and all of them benefit by a more accurate result. Okay, so that's one problem. The second problem actually is that anonymization is ineffective. So oftentimes an adversary can take an anonymized data set and combine it with other outside information in order to re-identify individuals in the data set. And this isn't just a theoretical attack. Actually, there are a few high-profile examples of exactly this type of attack. So the Netflix prize, does anyone remember the Netflix prize? Netflix released anonymized records of customer movie ratings, and they had this contest for data scientists to train better recommendation models for movies. And so they anonymized the data set according to best practices and released it to these researchers. Someone showed how to take movie ratings on IMDb and link those to records in the original data set in order to re-identify certain individuals. In another more recent example, New York City released anonymized taxi logs, and a security researcher went to celebrity gossip blogs and found pictures of celebrities getting into taxis, and then from those pictures it was trivial to link those rides to the original data set, right? Because he knew exactly what time they got in and from what location, and so he could figure out where they went and how much they tipped. So the point here is, who knows what other data is out there, right? And if you're relying on anonymization to protect privacy, you don't know what data set might be out there either today or in the future that would allow someone to do these sorts of attacks. So this is not a viable solution. Turns out there is a better solution, and it's called differential privacy. So I'll discuss this kind of at a conceptual level. This is actually backed by rigorous math, but I'll try to give you an intuition for how differential privacy works. The basic definition says that if you have any two databases that differ only in one user's data, so for example, Joe is in database 1 but not database 2, differential privacy says that any query you run on those data sets, or in our setting, any smart contract, the output against those two databases had better be essentially the same. In other words, there can be no way from the results to tell which of these databases was used to run the query. So this means there's no way to tell whether Joe was in the data set or not. So the differential privacy actually says that this has to hold true for every user and every data set. And so this is nice because it aligns very well with kind of our intuitive notion of privacy. That is to say, this guarantees that while I might be comfortable allowing my data to be used for some purpose, I don't want whatever you're doing with my data to be able to identify my record, or even whether I was in the data set or not. If you look in the literature, the formal definition is parameterized by what's called a privacy budget. So the nice thing about differential privacy is that because it's so general and such a strong definition, it means that from a user's perspective, if they know that differential privacy is enforced, they don't need to worry about specifically what computation is running, right? As long as this property holds, it doesn't matter what this query is doing. Now, the user might want to know anyways, but from their perspective, as long as the system can guarantee that this property holds, there's no downside to the user contributing their data. So they had better contribute their data anyways because the results would be the same. And so this is a nice definition, especially for blockchain. The problem is that it's just a definition. And so most of the previous work in this space is largely either theoretical or focuses on very specific applications. So Google actually uses differential privacy to track website visits in Google Chrome, and Apple uses it to track statistics about emoji use on iOS. So outside of these limited domains, there still today is no general purpose system for enforcing differential privacy automatically. So this was the subject actually of my dissertation, is building a framework to automatically enforce differential privacy for general purpose queries in an automated way. And so in the interest of time, I'll skip over some of these details. I want to point out, first of all, that the system is already deployed internally at Uber. So all internal queries that are submitted by a data analyst at Uber actually go through this system to enforce differential privacy. And other companies are starting to deploy it as well. And the entire thing is open source, so it's available on GitHub. So the idea is to integrate some of this work into the application layer, the development layer for smart contracts, so that developers who are building new smart contracts on sensitive data don't have to be security experts in order to build smart contracts that are, by definition, private and preserve privacy. In follow-on work, we showed how to build a system to automatically enforce differential privacy for machine learning models. So a data scientist defines a machine learning pipeline. The system automatically converts it into a new pipeline that, when trained on sensitive data, automatically enforces differential privacy. The nice thing about machine learning actually is that differential privacy is a very good fit for machine learning, because the goals of machine learning, of course, are not to overtrain on any individual's data. So by satisfying differential privacy, actually, it turns out, in certain cases, you can produce a more robust model that is more resilient against overtraining, because that's exactly the property that is trying to be addressed by differential privacy. That is, the output can't be overly influenced by any individual's data. So I talked about this as a top-to-bottom approach. Now you understand a little bit more about confidentiality preserving smart contracts and privacy preserving smart contracts. We think the combination of those properties together with increased scalability is useful for a wide range of different applications that fundamentally can't be built today on platforms like Ethereum. So here's a list of some of them. In a collaboration between Berkeley, ETH Zurich, and Stanford Healthcare, there's already an application that is built using this technology called Kara. So Kara is trying to solve this problem that today a lot of medical data is locked in these data silos, so it's underutilized. And the data is extremely valuable for research purposes, but of course the data is very sensitive, so oftentimes users and doctors are reluctant to share the data. And so Kara essentially is a data market that's built on blockchain that allows patients to input their data. In the current version, they scan it or input it with a mobile app. That gets stored in a smart contract. Researchers who want to train models on that data can pay tokens, and the smart contract will automatically train their model on the data. And the users get tokens in compensation for contributing their data, and the researchers get as output the trained model. So the nice thing about this, number one, is with confidentiality preserving smart contracts, users and researchers have assurances that even the workers that are helping to train these models won't be able to view or leak the data. And with differential privacy, right, patients don't have to worry about exactly what kind of model is being trained. They know that there's no way from the model that a researcher could even identify them. And of course, the importance of scalability, if you want to do something like machine learning and have this scale to millions of users and so forth, and you want it all to run on-chain without having to resort to off-chain solutions, for example, because you want to integrate with tokens, then it's important to have a platform that can scale to these sorts of more sophisticated workloads. So that's Kara, and that concludes my presentation. Thanks.
Are there any questions? A couple. Cool.
Hi, thanks for the talk. I'm wondering if you can talk a bit more about where you see data living, kind of like in its stagnant state, whether that's encrypted, whether it's on users' own personal devices. To me, the idea of just data, like personal data on a blockchain, doesn't really make sense. I don't see, like we have strategies for sharding, great, but ultimately data is something that should only ever live on devices people who actually need it. And so if you can just talk a bit about how you think about where data just resides in more of a stagnant state in these kinds of models.
Yeah. So of course, when the data's at rest, it needs to be encrypted if it's stored remotely anywhere, right? That's just a fundamental property of security. What I described doesn't presume necessarily that the sensitive data is stored directly on the blockchain. So the platform, in practice, the system provides flexibility for storing the data wherever users are comfortable with. And the smart contract has a way to ingest data from different data sources. So the platform can integrate with distributed data storage, allow users to directly send their data when they call into the smart contract. They could allow it to be stored on the blockchain, but there are other reasons why you might not want to do that. Scalability reasons in addition to privacy.
Back here in the back, hey.
Yeah.
When you were talking about the secure enclave, you had mentioned the smart contract executing inside of the secure enclave, and then you mentioned that that secure enclave would be offline. How would the results of that computation end up communicating back to an on-chain event in the case that it's offline?
Yeah, so there's software that runs outside of the enclave that is responsible for constructing the enclave in a secure way and getting the encrypted data into the enclave. Once the enclave finishes executing, it returns the results up the stack to the software that's running in the untrusted space. But the results are encrypted inside the enclave, so it's only the encrypted results that are sent back. And so the code that's inside the enclave doesn't have network access, but the worker that is actually running the computation runs some code in the untrusted space that is responsible for returning the results back to the blockchain.
So far as I remember what I've read about secure enclaves, especially provided by manufacturers like Intel, it was required to have some sort of collaboration with Intel about using the secure enclave with a certification or some process in place. Now, if you put that in an open source design and put it on the blockchain, wouldn't that be a very fertile ground for dark DAOs to arise and actually run maybe their own special version of a voting client inside that enclave in return for some ether that I get once I have the remote attestation that I voted in the way the dark DAO wanted from me?
So I'm not sure I fully understand the attack, but what you were describing earlier, yes, in Intel's current design, they are a central party that is responsible for verifying that enclaves are genuine and that these remote attestation certificates were produced by genuine hardware, because Intel is the one that embeds the private keys into the hardware. So Intel is the one that knows which private keys are valid for these signatures. As far as the attack on...
So the attack is actually pretty straightforward. So what could happen is that you promise someone to an ether if you vote on some whatever random system in his favor. And then the attacker provides you with a code that actually does the voting using your private key to actually authorize it, so that your private key never leaves your device. And then he makes sure that you run this code in an enclave, providing the secure attestation of the execution. And with that, you can prove that you voted in his favor, and he transfers the ether. And that's what's called a dark DAO. And you could use that as a perfect fertile ground to actually run these things.
So it sounds like what you're describing actually is sort of a more fundamental concern with any system that provides privacy.
Yeah,
right?
exactly.
In the same way that...
Not exactly any system, but when you use a secure enclave, you have virtually anything at your disposal to do whatever you want without being actually discovered by anyone. So you can actually trick any other system by actually building a network of colluders working together through secure enclaves. If you just put that on a public blockchain where everyone can just incentivize to run any smart contract in that enclave. And as far as I know, the only reason why this isn't happening already is that, and that is where my knowledge ends, is that there is some sort of verification by the hardware manufacturer before you actually have access to that enclave. I learned that from that hardware wallet, what's it called? The only one that actually uses an enclave at the point.
Yeah, so I mean that's sort of an application layer concern, right? And that could be mitigated with some
Yeah.
sort of stronger identity system. What you just described is actually not a failure of the platform.
No,
that's
it's
more
not.
collusion
It's not.
by right.
Yes. Do you have any ideas how to prevent that from happening? Because you don't want to introduce a trust model where you have to have someone certify your smart contract that is executed in your enclave. Right? Because you want it permissionless.
Depending on the specific application, there's potentially mitigations for that. I think what you're describing, again, is a sort of a fundamental property of any system that guarantees privacy and security, right? In the same way that, anonymous cryptocurrencies allow people to launder money without being traced, right? That doesn't mean that the technology is inherently flawed just because there are certain bad use cases that are enabled by, by strong privacy guarantees.
I actually got to wrap. This session's done. So, sorry, I know that there's a few more questions, but maybe, do you want to stick around just outside if there's more questions? Cool, thanks guys. Thank you.